Hey, how's everyone doing? Who all do we have here? I saw we had some people watching. We got some people here, right? Hey, what's up, Finch? Sorry you're live. Thought I'd pop in to say hi. Good to see you here, Finch. We're about to do some activity, some 320 activity, getting going with some 320 activity. How is everybody doing? Last stream of the day, last stream of the week. Faith, good to see you here. We're going to start out. I've got the activity loaded up. So let's go check it out and make sure everyone knows how to do some 320 activity. Let's check it out. So make sure you download the activity. Now, with the activity downloaded, you want to first do the following. Let's think about what this is going to do right here. I got the hiccups. You're going to right here and do the following. Install.packages. Go down here. Reg class. And I'm going to put this in the chat. Do it down here, though. This is usually where we install stuff. And installing is like downloading something to your computer. Kind of makes sense, right? So you're going to go to the CRAN server. And if you run this, I'll run it. Why not? Why not? Can't hurt anything, right? It's going to go here. Oh, really? Sure, restart R. So we're restarting R right here. It's going to install the package right now. And what it's doing is it's going to the CRAN server, getting the package and installing it on my computer. It's 2.8 megabytes. A lot of people get really scared because they see all this red text and they're like, oh no. I mean, it's alerting you to your computer has downloaded something, which it's all right. It's all right. We wanted it to do that. And so we've successfully installed the reg class package. So the reg class package is a package Dr. Petrie wrote, and it has in it the reg class functions. Once again, more red text, kind of alerting you to what's going on. Warning message, not that big of a deal, but these are all just messages and then a warning message. So if you're in 474, you know a little bit about messages and warnings right there that are inside this function that when the package runs. Now, a package right here, you can see reg class is loaded in. You can see your packages by going here and taking a look at what's inside of it. These are different functions inside of here. We have data frames and functions and all these great things that have loaded in with the reg class package. So a very important function that we have right here. And who all's here? Say hey in the chat. Remember, you get the points if you're here. Mubot tossing out those points to everybody right now. Who all is here right now? Say hey in the chat. We'll see who is all here to do some activity and talk about what's going on. This is a really good review right here to understand kind of how to use the associate function is the first thing we're going to start with. A little Sharvin activity. We got this. So we go right here. We've got the associate function. Now, Finch, good to see you. And so, Finch, do you know the format of the associate function? The associate function is how we see if two variables are associated. If you start typing it in, you will start to see it, and it says formula. So there's a very classic format we use when we do the formula function, or the formula argument, I should say. So what do we put inside of this? We have associate, and then we do blank, little blank, comma, data. My 474 students will be like, ah, yes. What do we put inside of this? What goes inside of that associate function right there? What do we have inside of the associate function? What do we put? I can explain how to do things, but you got to pause and you got to be like, do you know what to put inside the associate function? And I'm asking like the general form of it. Like we always put a this variable, tilde, this variable, comma, data equals. So you'll hear me say in class a lot of times, I've pointed out a few times, when we do the associate function, it's what, tilde what. It's actually got the code in if we go back in time in this. See if anyone knows. What are the thoughts? Take a stab, see if you got it. We take a look. It has nothing inside of it. Boom, William right there. Great job, William. Some 50 points. Y tilde x, comma, data equals. So that's the format right there. We choose a y variable, we choose an x variable, and then we do a data equals, and that's the name of the data frame. Great job right there, William. You are correct. Y tilde x, comma, data equals. So if you look at what it's asking us to do right here, it's asking us to use relationship status as the y variable. So that's the name of the y variable, and gender as the x variable. Now the problem is they don't have a data set loaded up. This is from the data set survey 11. It says up here, we need to load in survey 11. If this doesn't load, you haven't loaded in reg class. One way to know that this is from reg class is when you type survey 11, it's going to have reg class next to it. There's other things can come from like Aus beer, Australian beers, and well, that's not Aus beer. Oh, I reset R. Library FPP3, you don't have this. You can if you want. If you were to go here and look at a different data set like Aus beer, oh, it's Australian production, is it? There you go. Australian production, which has in it Australian beer production, is in the TISBL data. Australian air passengers is in FPP3. That's the name of the package this came from. Just like when you go over here and you type survey, these surveys are in the reg class package. If you don't see this, it's because you don't have reg class currently loaded up. Make sure to have reg class loaded up. That loads in the data, and you want to make sure you have library reg class. If it does not autocomplete, you don't have it installed. Check the start of this video to see how to install it, where we first installed reg class. So reg class is loaded and the data is loaded, and that puts it into the brain of R. You might be wondering, what is a data set? A data set is basically just like an Excel spreadsheet. Just looks like Excel with columns and rows. So we got here columns and rows, and it's basically an Excel spreadsheet. So now we go down here and we know what data we're using. Now I try to make my code look all pretty right here. I'm going to go and put this on a new line. You can do this with your arguments, and we get the association. Now, one thing I want to point out, because we haven't done this thoroughly yet, is I'm only making the graphic right now and running the association. This process behind me, every time I do it, is different. Why? Because these are all whats. These are all random whats that are being created right here. So every time I do this, it's different, and why? Who knows why every time I do this, this is different, but my observed data is not different, and also my observed discrepancy is always 9.138. That observed discrepancy right there is always 9.138, no matter how many times I run this. But these are different every time. Why? They're permutations created howly. What are these? Very important to know why these are different every time I run this. These are different every time I run this because these are what kind of permutations? Those are all whats. Boom, William right there. It's random permutations right there. So what you can do is you can actually go here and go to seed. Think about Minecraft, because Minecraft's awesome. And you can put in 320, and this will control the randomness. So if I rerun the code now with the seed, it's like being in Minecraft. When you put in a Minecraft seed, you get the same world every time. So the seed is going to control the randomness. It doesn't matter how many times I run it. It doesn't matter. We're going to get the same results every time we run it. This right here is, I think, 500 permutations. 500 permutations by default, but watch this. Permutations as a new argument, and let's go here and put in four permutations. I don't know how to type. When you take a look at this, the p-value is going to be the amount of permutations that are as extreme or more extreme than our result. This is our observed discrepancy of 9.13. How many of these random permutations, created by random chance, are as extreme or more extreme than our observed result? How many out of the 4? So here's our result. How many of these are beyond this red line? How many of those random permutations are beyond our result? Which then we could figure out the probability of getting a result as extreme or more extreme than our result by random chance, because these are by random chance. How many of them are as extreme or more extreme than our result? 0. Benson, great answer right there. You're right, it's 0. So with 0 being as extreme or more extreme than ours, the p-value is estimated to be 0. But watch this. What about if I did 20 permutations? Oh, we didn't get lucky. What about if I did 50? Ooh. That is one permutation right there. The height of it is how many are in there. But 1 out of 50 is how much? 1 out of 50 is what percent? Think about it. 1 out of 50, which is how many of the random permutations are as extreme or more extreme than ours. And this is 2 permutations because the height is 2. That's another 2. That's another 2, 2. And is that 2? Yeah, looks to be 2. But that is definitely 1. I can confirm by looking over to the side and seeing the estimated p-value. 1 out of 50 would be what? Like the probability of getting a result as extreme or more extreme than this result right here is going to be 1 out of 50, which is right there. That is how the p-value is being obtained, literally by doing 1 out of 50. So if I were to increase the permutations more, now we have 1, 2, 3 results, and look, 3 out of 100. At a certain point, there's too many to count, or it's really hard to say, like, well, that's 1, 2, 2, 1, 1. It's really hard to tell. There, in this instance, are 3.2%. The amount of permutations that are as extreme or more extreme than our result are 3.2%. But we run into a problem. The problem is this. We want to know if there is an association between somebody's gender and whether or not they have a significant other. So when you look at this right here, what do you notice about males and females? Males are a little bit more likely to be what? We can look at the conditional distribution. Given someone is male, it looks like they have about a 50% chance of being this. Given someone is female, it looks like they have about a 39% chance of being this. I've already looked at the numbers. Given someone is male, they have about a 50% chance of being this. And given someone is female, they have about a 39% chance. So that's one of the key differences I see there. Married is about the same for both groups. I see a discrepancy right here. There's a difference in the blue. So what's going on right there? What's going on? That might be indication of some sort of association where males are more likely to be this. Sorry, males. Might be that males are a little bit more likely to be what? Unless you want that, then it's happy music. And it's all good. And it's just like, yay. I don't want that. I don't mean this little tiny green group. Males are a little bit more likely to be what? What would be males? Males have a little higher probability. Given somebody is male, let's go look at the numbers. Given somebody is male, they have a little higher probability. These are the conditional displays. It does say marginal, but it's also the conditional. This is given somebody is male, the probability is a little bit higher that they'll be what? Given somebody is male, they have a slightly higher probability. And see, we can check the numbers here. We could also compute this. We need to show how to compute it probably too. They have a little higher probability of being single. But if we go back to here, let's try computing it. This would be for only males. We have 285 males and 143 are single. So there's the probability we just obtained right there. That is the probability given someone is male, the probability they're single. Females are less likely to be single, this blue graph right here. And so we see a difference in the conditional probabilities. We also need to know how to things like finding the expecteds. That's key for the test. This is straight teaching to the test right now. To find an expected, let's show the trick for it. To find the expected, we'll go here and we'll take row total times column total over grand total. Teaching to the test here. Not that I always do that. But if you were to take this, and I can't draw, and divide by this, you will have now found out the probability of being female and being in a complicated relationship, the expected count of female in a complicated relationship. So we go ahead and do this and check our numbers. 343 times 36 divided by 628, and we get 19.6, and that's going to round up right there to 19.7. That is how we find these expected counts. It's all the row totals times column totals or grand totals, and we take all of those right there, and then finally we get the cell chi-squareds and add those up. Make sure to review the notes on the adding up the cell chi-squareds, which gives us the discrepancy right here, which is actually a chi-squared test statistic. Fun side note, the graphic behind me is a simulated chi-squared. If you do enough permutations, you will basically see virtually identical to what we would see for a chi-squared with 2 degrees of freedom. This is a 3 by 2, turns into a 1 by 2, and that is a simulated chi-squared with 2 degrees of freedom via random permutations. You notice right here, we've actually increased the permutations, and what changes as we increase the permutations? The p-value could go up or down. The p-value doesn't have to stay in one spot. It's random where the p-value is at. But here's the thing. Although the p-value can go up or down, by increasing the permutations, we'll get a better estimate. And then what do you notice? What is smaller? Because we're trying to figure out what the p-value is by simulations. So who in the chat can tell me for 100 points right here, what is getting smaller? If I increase the permutations, which I have a lot of permutations right here, the p-value can bounce around because that's just randomness, because the random permutations will give different random results. But if I go here and go to like 50 permutations, take a look at what changes. We get a p-value of 0, a smaller p-value, but something changed. Now I have less data to do my results with. Less data means I'm going to have a what down here. So here's with a small amount, and here's with a large amount. Watch what changes. The p-value is pretty random, could be pretty much anywhere. But when we increase the number of permutations, What changes? What changes about this? Increasing the number of permutations will give us a better estimate, and a better estimate has smaller uncertainty. Smaller uncertainty means smaller margin of error when we're estimating this p-value. That means this confidence interval right here is tighter, because I'm saying I believe the true p-value, because we're trying to find out if this is statistically significant. I believe the true value p-value is somewhere contained in the interval 0.021 to 0.03. And you know what's so great about that? That interval does not contain 0.05. So I'm saying I think these results are statistically significant. I have confidence these are statistically significant. I'm 95% confident the true p-value is in this range, so I do think it is statistically significant. Now, the reason we set the seed on this because we don't want these results to change. Like if I send this to someone, I want them to look at it and say, hey, these are the results I got. If I set the seed, the results will be the same for me and for them. If you don't set the seeds, you will get randomness every time. This is randomness, but the randomness has been set that I can control, that we will get the same randomness. It's kind of set randomness. Bit interesting right there, right? Does this mosaic plot suggest an association? Well, one, our results now are statistically significant and we're confident about it. Two, there does seem to be some sort of light association where males look to be a little more likely to be single, a little less likely to be dating, and a little less likely to be it's complicated. Females are more likely to be in the groups it's complicated in dating and less likely to be in the groups it's single, especially when we look at the conditional distributions right here. Males and females both had a very low probability of being married, a little bit around 3% for both. Very little bit smaller for females, a little bit higher for males. But overall, the big differences look to be between singled females and singled males, more single males, and dating females, dating males, more dating females, and a little bit more complicated females than complicated males. And that's where we see the discrepancies most prevalent in this graphic. And I would quote the numbers right there. So what is the estimated discrepancy? We covered a lot there. We've added the permutations, covered that. And there's the adding of the permutation. Question 2. We should do a little bit more after this. Go at least 45 minutes tonight. Who all's here? Who all's here? Question 2 right now. We'll put a break in the video so I can mark this. If you're here in the chat, say, hey, so Mubot can give you some points. It's been a long day. It's been a long week. Who all is here in the chat? We had here William and Benson here earlier and Finch. Good to see everybody. Long day. Sometimes I fear I'm not streaming. I had one class where I talked for like 10 minutes and then everyone's like, when is this going to start? And I was like, it started. And then they were like, it hasn't started. They didn't hear that though. They're typing in the chat. So here we are. Download the friendpot fdat to your BAS 320 folder, which I think I've already downloaded that. That's a data file basically. What's up, Benson? Good to see you. Benson, another 50 points. Did I press it? I didn't press it. So download that to your folder or wherever this RMD is. Make sure you put it in the right spot. And read it into using the read.csv and call it FF. We already got the code set up for you right here. Now, one thing I want to point out is that the read.csv function works on multiple things. We're using it on a DAT file, which is that file. Laney, good to see you here. And we are storing it into the object FF. What is this going to look like? It's going to look like an Excel spreadsheet. So this is somebody's friendship score based on their attractiveness, their actual sexuality, their apparent race, whether cleavage is showing, face symmetry, fashion score, fitness score, gay score, glasses, groom score, hair color, all these things right here. A lot of interesting variables. Skin clear score. Well, I don't win that. So smile, piercings, all these things right here. Pretty interesting data set, kind of a social psychology data set. And people are rating these individuals' attractiveness and their friendship scores and all these different things. Pretty interesting data set to kind of work with. Ooh, let's look at a histogram and a QQ plot. Why do we look at QQ plots? Very important question right here, a QQ plot, and this goes to Stat 201. And let's look at the friendship score. So let's go to our data frame and $sign to go inside of it. And we're going to look at the friendship score, and let's look at the histogram first. I don't know. Why do we look at a QQ plot now? Let's look at a QQ plot of it. Coach is QQ. And the QQ plot is known as a normal quantile plot because we want to know if this data is what? What's the point of a QQ plot? Really great review right here. What is the point of a QQ plot? And there's answers towards the end of this. What is the point of a QQ plot? Why would we ever look at this QQ plot? And the answer is going to be on the bottom of the screen. What do you think? Why would we look at a QQ plot? A QQ plot is going to help us determine whether or not this data is what? A QQ plot, read the bottom right there. It's a huge help on the bottom if you read the bottom. It's a huge help. The QQ plot is going to help us determine if this data is what. Why would we look at this plot? So why do we look at that plot? Normal, Laney, great job. Some points in the chat right there. And so we determine whether or not it's normal. So if you have normal looking data, like let's say you have data, this is just an example. If you have data right here that looks like this, then if you run a QQ plot on it, the QQ plot's going to follow the straight line pretty well. We could go down to just like 50 points to make it look not as crazy, or as many points in there. So if you have data that looks like that, it's going to follow the QQ plot. You know, ours kind of looks like that. Kind of. That was 59. And if you have data that's not normal, let's go to data that's exponential, random exponential numbers. This is just a code to generate random exponential numbers. If you have data that's not normal, your QQ plot's going to look all kind of bent and not normal. So once again, a QQ plot that follows a normal histogram will follow the pattern right here and follow the line down the middle. That's good indication of normality when it follows this line down the middle. These dashed lines are kind of your like, you don't want them outside the dashed lines. So you will sometimes, these are all normal data right here. So you can get points outside the dashed lines, like right there. So this is actual normal data. I'm generating random normalness right now, or normal randomness. And so this is normal data, but it's outside the lines. So it's kind of like, But here we go with data that's not normal, and you can see it clearly violates. It clearly goes outside the dashed lines. You kind of want to look for that. You want to be a little forgiving. Like, the better it is, that's good. But when you start to see this one, I might almost let that one... See, I know these are not normal, so it helps me decide. Like, this one's obviously not normal. Some of these could pass. That one's got a big outlier over there. This one almost could get away with it. This one I might let pass. And it's not actually normal. So I might let this one pass. If we have more data, it's going to start to really deviate because you'll have more outliers from non-normal if it's really not normal. So with this right here, why are we deciding if it's normal or not? The decision on whether it's normal, and that's a big choice right there, the decision on whether it's normal will decide what? What will the decision on normal or not normal decide? What will the decision on normal or not normal decide? Why would we decide to use normal or not normal? Why are we going to make a choice that this looks... It's got some low outliers down here, got a little bit of odd skew nature to it. Like if it goes bendy, if it pushes in, it's got skew. Mainly you're just looking for, does it follow the red line? And these right here are going to be more of outliers from what we would expect due to normality because they're far away from the red line. I don't know. It's borderline. Because if it's not normal, we're going to use the median as the measure of central tendency due to outliers and skew. But if it is normal, we can use the mean because the mean is something we want to use if there's not outliers. It's a bit iffy right there. Determine if there's an association between friendship score and someone's actual sexuality. Use seed 320. So let's go ahead and check this out right here. Let's go to the association code right here. And associate. We're going to take someone's friendship score as the Y variable because this is what we want to understand. We're going to take actual sexuality to see if that explains it. And then remember, Y tilde X, comma, data equals. And then we're going to put in here the FF survey. And then last but not least, we do need to put in a seed of 320. And that should do it. It's going to use the 500 permutations by default. And what do we see? This is a little bit different right here. This is different output. The top graphic is showing us box plots, side-by-side box plots, categorical X, quantitative Y, where we're looking at somebody's actual sexuality divided up into gay and straight, and then the friendship score divided up here into scores about 1 between 5, I think. And here's the mean. You don't always get that in a box plot, but these ones supplied it. Then the median's right here, so there's maybe a little skew to that. There's the left skew down there. So their mean's a little lower. There's the mean right there. There's the median. And that's what we're really going to be looking at is the central tendency in either mean or median. I'm going to go with mean, but you know what? The decision's kind of moot because that means it doesn't matter. It doesn't matter! Because down here on the bottom, I can actually tell you the p-value for these. Looking at these graphics down here, the p-value is the probability of our result or results more extreme occurring by random chance, given the null is true. And let's take a look. Take a look at these graphics, and you will see our result. This is your result right here in the red line. Let's make it the red line. Your observed result is this red line. This is our result. And we are seeing a very small discrepancy. Our result is a very small discrepancy. But I want you to look at this. The results that are as extreme or more extreme than ours is what percent of the curve? What percent of this curve is as extreme or more extreme than our observed result? So once again, right here, we have our result. And this is the test on the averages. That was the mean ranks. The median's the same over on the other side if you want to see this, but over here. And so what do these p-values look to be if we look at the percent of results that are as extreme or more extreme than ours? See if you can figure this out. All of these p-values right here are going to be very close to what? Because our result is very small. We have a very small discrepancy. The discrepancy that you are seeing is a numeric calculation of the variation we see between the means compared to what we would expect. So we can compare these values, and they're very close. Or we can compare these medians, and the medians are basically on top of each other right there. So we're seeing basically a discrepancy, or in this instance, an F statistic for the means of about 0. And that's observed down here on the bottom. When you look at our observed discrepancy for the means, is about 0. It's very close. It's like 0.2 or so. So when you think about this, what would the p-value be for this? Who knows the p-value? The p-value is the probability of getting a discrepancy as extreme or more extreme than our result due to random chance, and these are all random chance. So what percent of these random chance permutations, about what percent are higher than ours? About what percent of the random chance permutation are higher than ours? Who knows how to do this? What percent of the random chance permutations look to be higher than ours? Decent test question. The p-value here is going to be the percent of random chance permutations that are as extreme or more extreme than this red line, and the percent of random chance permutations that are as extreme or more extreme than this red line. And for this test, this one has another p-value. The discrepancies are as extreme or more extreme than this one. So what would the p-value be? The p-values are all going to be very, very close to what? All of the p-values are going to be super close to 1 because all of the random chance discrepancies are as extreme or more extreme than ours. And take a look. If you look at the p-values, we'll regenerate the output. We have a seed, so it won't change. I just don't want it to wrap around the screen. All the p-values are closer to 1. This one is exactly 1 because the discrepancy is basically 0. If you look, this is the discrepancy as a standardized metric, and that stands for 0.0000002483. That is a ridiculously tiny discrepancy. And basically all discrepancies by random chance were as extreme or more extreme than this. Kind of nice to know that somebody's friendship potential is not well explained by their sexuality. Good news there. And these discrepancies are rather small and likely by random chance. Down here in this result, we'd want to know if we're confident. Are we confident that the test we did, I picked the means because I said, these QQ plots, if we go back and look at our QQ plots, my QQ plot looks kind of normal. This is an iffy one. It's iffy. You could say, nah, this is a little too bad. I don't like these. Or you can say, that's okay. This is one of those ones that's on the fence. Not so sure which way it goes. And so right here, we can see that I picked averages because I said it looks normal enough, follows the red line close enough, just barely. I'm being a little forgiving to it. And it is not statistically significant, and I am confident in this result. Why am I confident, and this is a review question now, that my test of differences in the means is not statistically significant? Why am I confident that my test for the differences between the means is not statistically significant? Why would I be confident and be like, I'm confident that this is not statistically significant? What about that interval right there estimating the p-value brings me confidence to be like, yep, that's not statistically significant? Why would I be confident about that? Who knows? So we need to look down at the bottom if you're thinking about it. If you're like, wait, why would I be confident it's statistically significant? So when we're trying to estimate the p-value, we want to know, is the p-value above or below 0.05? Yes, completely great job right there, Lainey. Yep. The whole entire interval is completely above 0.05. Now, you could have instances where the whole p-value is below 0.05. So we saw some earlier. We go back and look at other tests. In this instance right here, the whole entire interval, that one does not, that one contains 0.05. This interval is completely below 0.05, so I am confident that this is statistically significant. This interval right here, it contains 0.05. Since this interval contains 0.05, I'm not sure whether it's statistically significant or not. Does that make sense, Laney? Or is it Lane? Sorry if I got it wrong there. That this interval, I'd be like, well, the p-value might be as low as 0.018, or it could be as high as 0.051. I don't know. Is it statistically significant? Maybe, probably, but I'd like to increase my permutations, and that's what we do if we have 0.05 in the interval. And now after I increase the permutations, I say, okay, with more permutations, that's fewer. With more permutations, where's my more permutations? Oh, that's fewer still. With more permutations. Definitely want it with more permutations. Ah, here we go. This time I ran it with 5,000 permutations, which gives me a much better estimate. And now I'm 95% confident the p-value is between 0.023 to 0.032, and this does not contain 0.05. So I can say, yes, my results are statistically significant, p-value below 0.05, and yes, I do think I am confident in this. But in this instance, I am confident in these results here not being statistically significant. The first part up here with the p-value answers the question, is it statistically significant? And then the intervals answer, are you confident? In all instances down below, we are confident it is statistically significant because none of these intervals contain 0.05. So there's a specific number you should increase to test most permutations matters. And you got my name right. Oh, awesome, Lane. You're welcome. There, basically, you could be like, like 500 is not bad. And then you could just increase to permutations of like 5,000 if you want. It'll just make the intervals tighter. And usually 500 is fine. But then if you want 5,000, if you notice, it actually just takes more time. So that's why you don't have 5,000 as the default. The default is 500. If you were to go in here and do 2 permutations, watch how long this takes. You ready? Done. It just blinks because it's generating these random results behind me, and you can actually see the random permutations being generated. So the answer of how many permutations do we need would just depend. In this instance, 2 is really not a good way to estimate it. Instead of generating 2, you see it's doing the bottom graphics, it's generating 2,000 now. And that's what the bars are right here, are all the random permutations. But we do get a result that does not include 0.05. If you do 2 permutations, you'll probably include 0.05. You don't. It's just really not that significant. It's really, wow, that's interesting. With 2 permutations, you can get not significant results. 1, oh, you see, now look. Now it contains 0.05. Even though my p-values are 1, meaning that what I saw was very likely due to random chance, my p-values are 1, but my interval for the p-value is ridiculous. You would never run one random permutation. It just depends on how iffy the results are. So if you get 0.05 in the interval, like we have right here, you could increase it, and we increase maybe to 100 permutations. And with 100 permutations, we actually have a not significant result in confidence. 500 is a good default, though. But the reason we run 500 is instead of 5,000 is computer time, because it can, some bigger problems can take a lot of memory if we're running like a lot of data to do the permutations with. That might be it. Let me take questions. Here, we'll go to the main screen. Not that crazy of a lab this week. So I was like, we got this. What questions do you have right now? You're welcome. Were you able to get 100 on it? If you're working on a specific question, be like, hey, Brian, can you work on this question? People who are here get to ask the questions and say, can you talk about this one? Can you talk about number 2, number 3, number 4, number 5? If hopefully people are getting hundreds on the quiz, what questions do people have? Knowing how to read the output is key. We went over a lot of the reading of the output tonight, so I'm hoping people can use this video to review when it comes time for the test, to be like, how do I read the association output? We did 2 categorical variables to start, and then we went to a categorical X and a quantitative Y with the box plots and looking at either the mean or the medians. So if you're looking at a really good, just kind of quick review right here, 2 categorical variables is displayed with a mosaic plot, and we want to look at the differences in the conditional distributions to see if there's an association. When you do a categorical X and quantitative Y, like we were just doing, that's going to be side-by-side box plots, and we want to look to see if the data is normal, the Y variable is normal, to either compare the means or the medians. And yeah, that's what we're just doing right there. was like, that's short activity. We got it done though. Swing by every week. I think this was a big exam week. I'm gonna go take a break, I think we're good to go. Puppet Shark, you had a good night? You have fun? Puppet Shark had fun. With that, we'll be back, everybody, on Monday. I'll see everyone then. Bye for now. Bye.